Have you ever felt the ground tremble as a freight train roars by? Now, imagine trying to stop it. We're not talking about a car or a truck. This is over 10,000 tons of steel, barreling along at 50 miles per hour. The challenge? Momentum, mass times velocity. Even at low speeds, a train's momentum is enormous. To stop it, all that energy must be dissipated, mostly as heat through friction. But a train isn't a single block of metal. It's a chain of heavy cars that must stop together, smoothly, without crashing into each other. That's where brakes come in, the most critical safety feature on any railway. The real engineering marvel isn't making a train go, but making it stop, safely, reliably, every time. The brakes must be powerful, reliable, and fail-safe. If something goes wrong, the system should default to stopping the train. In this video, we'll explore the genius of train brakes, focusing on the air brake system, and see how different types of brakes work together. We'll also look at what happens when things go wrong, and the modern tech that keeps disaster at bay. It's a journey into the hidden engineering that lets our world move and stop safely. Let's dive in. Scene transition. The backbone of train braking is the Westinghouse air brake, invented in 1869. Its brilliance, it's fail-safe. If air pressure is lost, the brakes automatically engage. Here's how it works. A compressor in the locomotive fills a main reservoir, sending pressurized air through a pipe along the train. Each car has its own air reservoir, kept full by this pipe. As long as the pipe is pressurized, brakes stay off. To apply brakes, the engineer releases air from the pipe. The drop in pressure triggers each car's triple valve, which sends air from the car's reservoir into its brake cylinder. This pushes brake shoes against the wheels, creating friction and slowing the train. Every car brakes at once, preventing dangerous pileups. If the pipe breaks or disconnects, pressure drops instantly. Every car slams on its brakes automatically. The system's genius is its simplicity and safety. Any failure means the train stops. That's why the Westinghouse air brake is still the gold standard. Air brakes are just the start. Modern trains use multiple braking systems for safety and efficiency. Dynamic brakes turn the train's electric motors into generators, using the train's own momentum to create resistance and slow down. No friction needed. The generated electricity is usually burned off as heat in resistor grids, but on newer trains, regenerative braking sends that energy back into the power grid or charges batteries. This saves energy and makes frequent stops, like in subways, much more efficient. High-speed trains often use disc brakes, giant versions of car brakes, for extra stopping power. Trams and light rail sometimes use magnetic track brakes, powerful electromagnets that clamp onto the rails for emergency stops, even in slippery conditions. Each system has a role, working together to keep trains under control. It's a layered, redundant network. If one system fails, others are ready to step in. This teamwork of technology is what makes modern rail travel so safe. Braking isn't just about stopping, it's about control, efficiency, and safety at every mile. Scene transition. Even the best systems can fail, so engineers have built in layers of protection. Air leaks are a common issue. Tiny leaks can reduce braking power or trigger unwanted stops. Modern trains have sensors to detect pressure drops and alert crews before problems escalate. Heat is another enemy. Friction brakes can overheat on long descents, causing brake fade and reducing effectiveness. That's why dynamic and regenerative brakes are crucial. They slow trains without overheating the main brakes. Cold weather can freeze moisture in airlines, so locomotives use air dryers and robust materials to keep brakes responsive. For extra safety, advanced train control systems like positive train control use GPS and computers to monitor speed and position. If a train is going too fast or risks running a signal, the system can automatically apply the brakes. These digital safeguards help prevent human error and add a final layer of protection. Safety is never left to chance. Stopping a train is a daily miracle of engineering. A 150-car freight train at 50 mph can take over a mile to stop, about 20 football fields. That's why you should never try to beat a train at a crossing. The laws of physics can't be cheated. On steep grades, runaway ramps and safety sidings provide a last line of defense if brakes fail. At stations, engineers blend dynamic and air brakes for smooth, precise stops, sometimes with automated systems for extra accuracy. Every safe stop is the result of over 150 years of innovation, from Westinghouse's air brake to today's smart controls. These systems are the unsung heroes of the railway, working in harmony to control immense forces. Thanks to them, every journey can end safely, no matter the cargo or the distance. End.